Okay, another type of reaction, or really an extension of reactions, is a redox reaction. A redox reaction, so the word redox is actually short for oxidation reduction. So like the reduction part and the oxidation part put together is what we call a redox reaction. So let me just tell you first, I'll teach you what an oxidation reduction reaction looks like after I teach you about oxidation numbers, because you can't identify a redox reaction without knowing what an oxidation number is and how to assign it. Now, this is going to seem like a lot of rules at first, but just know that these rules are printed in your notes, and you get used to them. The more practice you do, the more you get used to the rules, and you're not having to go back and look at them so much. So the whole idea behind oxidation numbers is that they are based on the transfer of electrons. So it's however many electrons are lost or gained in the process to form a bond. So the rules for assigning oxidation numbers, you actually know a lot of them because they correspond to the charges that we've been using for ionic compounds. But then when it comes to molecular compounds, the rules can kind of get a little bit tricky. So we are going to go ahead and explore those rules now. The rule number 1 is the oxidation number of any uncombined element is 0. I have a few examples for you. Na has an oxidation number of 0 when it's by itself, and then any diatomic, like hydrogen, H2, it has an oxidation number of 0. So the oxidation number again means that there is no loss or gain of electrons to form the bond. So if you have an oxidation number of a monatomic ion, monatomic meaning a single element represented off of the periodic table that is in its ion form, the oxidation number is the same thing as the charge. So if you locate chlorine or on your periodic table, and we know chlorine ion is called chloride, we know the oxidation number is -1. Rule number 3, the more electronegative element in a binary compound, binary meaning a compound with 2 elements only, is assigned to the number equal to the charge it would have if it were an ion. I think it's easier to understand that statement through an example. So if I have a binary compound like this, 2 elements, NO, this is not necessarily an ionic compound, it can be a molecular compound also. We look at the more electronegative element, which really means the element on the right side, and then that element attains the oxidation number that matches its charge. So oxygen, you know, as an ion, oxide has a -2 charge. That's not new to you, but what we're going to learn how to do is figure out the oxidation state of nitrogen in this compound. So oxygen is usually -2 unless it's a peroxide as -1, and you did not learn about peroxides in this class, so you have nothing to worry about. Every time you see oxygen, it's usually -2. Rule number 5, the oxidation number of hydrogen is usually +1 unless it's combined with a metal. So this is a case where you find hydrogen in the front of a formula or in the back of a formula. If it's in the back of the formula, kind of acting as an anion, it is going to have an oxidation number of -1. If you find hydrogen in the front of a formula, which we typically see hydrogen in that way, the oxidation number is going to be +1. And then groups 1 and 2 elements and aluminum have oxidation numbers of +1, +2, and +3 respectively. And here are some examples. Calcium has an oxidation number of +2, and that is not new to us. Those rules in number 6 here, they really correspond to the same rules that we know for charges. Here's rule number 7. The sum of the oxidation numbers of all the atoms in a neutral compound equal to 0. So it's almost as if we're putting all of our rules together and we're really starting to determine oxidation numbers for certain elements within a compound. So within this compound of NO3, nitrogen trioxide, what I have here is I have an equation set up for us to determine the oxidation number of nitrogen. Now we have 1 nitrogen, that's representing my X. We have 3 oxygen, so I have 3 times the oxidation number of oxygen, which we know is -2, and the whole thing is equal to 0. And then the last rule, I believe this is the last rule, the sum of the oxidation numbers of all the atoms in a polyatomic ion equals the charge of the ion. So really similar to number 7 that you saw above here. It's really similar, except whenever you have a charge involved, that is going to be what the equation is equal to. So let's say in number 8, I asked you to determine the oxidation number for phosphorus. Phosphorus is represented as X, right over here. I see 4 oxygen, so I have plus 4 times the oxidation number of oxygen, which is -2, same as the charge for oxygen. And then I have this whole thing set equal to -3 because the charge is -3. So those are the rules for oxidation numbers. So here's an actual example. I might ask you to determine the oxidation number for carbon in this formula of carbon tetrachloride. So here's what you would do. You can set up an equation much like I showed you on the last slide. And what we know about chlorine chloride's ion is that it has an oxidation number of -1. We're trying to figure out the oxidation number of carbon, so I'm going to call that X. We are going to add that to 4 times -1 since there are 4 chlorines there, and we're going to set this whole thing equal to 0 because there's no charge. Okay, so this is our equation, and we're just going to use some algebra to help us determine the oxidation number for carbon. Now, I've worked out every single one of these examples showing you the algebra step by step, so if you're weak in algebra, this would hopefully help you out in understanding the steps a little bit better. So what I'm going to do first is I'm going to go ahead and simplify a little bit of my equation. I'm going to go ahead and multiply these two things together, 4 times -1, and I get -4. I'm going to go ahead and bring down the 8 equals 0. And what I know from algebra is that whenever I'm adding a negative number, it's really like I'm just subtracting. So really this just tells me x minus 4. So I'm going to get rid of that plus sign there to simplify things. So now I have x minus 4 equals 0. And I'm trying to get x by itself. So whatever you do to one side of the equation, you have to do the other. So I'm going to subtract, I'm going to add 4 to each side because I'm trying to get rid of this -4. And when I add 4 to each side, I end up with x equaling +4, which is now the oxidation number for carbon. So the oxidation state of carbon is +4, and it lost 4 electrons. Here's another example. I have H2S, and I've underlined S because let's say I'm asking you to determine the oxidation number of sulfur. So what I know about hydrogen is that when it's in the front of a formula, it has a +1 oxidation state for each of the hydrogen, to be more specific. And so when I set up my equation, I have 2 times +1 because there are 2 hydrogens in the formula. I'm going to add that to X because X is my sulfur. And I'm going to set the whole thing equal to 0 because there is no charge here. I'm going to go ahead and simplify my equation a little bit. 2 times +1 is just 2. I'll bring down my plus x. I'll bring down my equals to 0. So I have 2 plus x equals 0, and I know that I want to isolate x on one side of the equation, and you always do the opposite of what the numbers, what the order of operation is. And so since this is like being added to 2, I'm going to go ahead and subtract 2 from both sides. You always do the opposite to isolate the unknown variable, which in this case is x, and that leaves me with x equaling -2. Now, all of this stuff here is side work. You really don't have to do all of this. Eventually, some of you guys are going to be gifted enough that you can just eyeball the equation without having to write it out, but sometimes it is helpful to write it out. So let me tell you what this -2 represents. It tells us the oxidation state of sulfur, and it tells us that oxidation state of -2 tells us that sulfur has gained 2 electrons. And so some of you guys, I've noticed that you've just kind of memorized that whenever you see a negative charge, that means it gained electrons. Whenever you see a positive charge, that means electrons were lost. Here's our next example. We see a little bit of a difference here because there is an overall charge for this polyatomic ion. So sulfur is our unknown here. And I'm going to go ahead and call that X, but I know that whenever I see oxygen, that has a -2 charge. So X is my sulfur. I notice there are 3 oxygens, so plus 3 times -2. I'm going to set the whole thing equal to -2. I'm going to go ahead and simplify this. I know that 3 times -2 is 6, so I'm going to bring down the X. I'm going to simplify that to -6. and the whole thing is equal to -2 again because of that charge. And now I'm going to go ahead and try to isolate x on one side of the equation. I know that when I see x plus a negative number, that really means the same thing as x minus 6, so I'm just going to simplify things more that way. And to isolate 6, I need to get to isolate x, I need to get rid of this -6 on the same side, so I'm going to do the opposite. Since it's a negative, since it's like subtracting 6, I'm going to go ahead and add 6 to both sides. And then I end up with x equals positive 4, because -2 plus 6 equals positive 4. And if you're not really good at adding and subtracting negative and positive integers, go ahead and use a calculator. It's okay. It's there for you, so you might as well use it. So that positive 4 tells us that the oxidation number for sulfur is positive 4, and that means in the reaction, in creating this bond, 4 electrons have been lost through that process. And then here is more practice problems. I strongly advise you to go ahead and hit pause first so that you can practice them out, and then continue watching through to the end. But if you're ready to keep watching, I'm just going to kind of click through so you can watch your steps, but press pause anytime if you want to continue on the problem at any point, because practice always does make you better. It's not enough to just watch what happens and then expect yourself to replicate it right away. So here is practice A. I'm solving for boron here. There are 4 boron in this formula. There are 7 oxygen with an overall negative charge. Each oxygen has a -2 charge, so let's set up our equation. I have 4x plus 7 times -2 equals -2. The -2 is the oxidation number for oxygen, 7 atoms of oxygen. 4 is my boron, and x is my unknown oxidation number for boron. Through some algebra, I'm just going to go ahead and multiply these two out. I have -14 equals -2. I'm going to go ahead and bring the -14 to the other side by adding 14 to each side. And then when I do that, I have 4x equals positive 12. And to isolate x in this scenario, I'm going to do the opposite. This is 4 times x, so I'm going to divide both sides by 4. And that leaves me with x equals positive 3. This tells me the oxidation number of boron, in this equation at least, is lost and is positive 3, and it lost 3 electrons. Here's HNO3, better known as nitric acid. I have hydrogen with a positive 1 oxidation state because it's in the front of the formula. I don't know what nitrogen is, but I do know oxygen is -2. I do not see an overall charge, so I will set this equation up equal to 0. And here is my equation. This one's a little bit longer than the ones that we've seen so far. I'm going to go ahead and simplify it down a little bit. I'm going to go ahead and combine these two things on the left side. So I'm going to combine the positive 1 with the -6, and that comes out to -5 plus 0. You add 5 to both sides, and x equals 5. Alright, so now we're going to talk about something called an oxidized species and a reduced species. So you're just going to be asked to identify an oxidized species and a reduced species in a reaction. And in order to be able to do this, we have to determine the oxidation state. So that's why we just did that oxidation state, assigning oxidation number lesson before doing this. So here are some helpful acronyms. OIL-RIG. OIL-RIG is an acronym that represents oxidation is loss of electrons, and then RIG is reduction is gain of electrons. So whenever we have an oxidized species, that means it lost electrons. A reduced species means that it gained electrons. And so I also came up with this helpful acronym, not really an acronym, but like a little saying, oxymopo, because I feel like this is easier to identify which one is oxidized, and the oxidized species becomes Mo positive. So let's use that saying to help us identify the oxidized species versus the reduced species. So here's an equation. In this equation, we basically have to go through first and identify the oxidation states of each of the substances. So these are free elements. Do you see how they're just elements? And this is like rule number 1, I think, on your list of rules. Each of these oxidation states for the first two substances, first two reactants, are 0, just because they are elements by themselves. When it comes to the oxidation states of each of these guys, remember that chlorine is always -1. And we can figure out iron based off of all those practice problems that we just did, and iron is +3. Here is the work to show you how to determine the oxidation state of iron. So the next thing we want to do is we want to determine the oxidizer by identifying the element that becomes more positive, or MoPo. So if we compare iron before to iron after the reaction, do you see how the oxidation states go from 0 to +3? That's getting more positive, or MoPo. And chlorine goes from 0 to -1, so it's becoming more negative. So this is what we're working with. Iron goes from 0 to +3, chlorine goes from 0 to -1. Iron is the oxidized species, and chlorine is the reduced species. So not only have you just now learned I can call this an oxidation reduction reaction, this is a redox reaction, but now we have also identified which species was oxidized and reduced. Not all equations are redox reactions. It's just when you notice that certain elements change their oxidation state in the middle of the problem. Okay, so in this example, I'd like for you to hit pause, and I want you to try to identify the oxidation numbers for each of these substances first, and then we're going to identify the oxidized and reduced species. So I'm going to keep going with this, and what I know is about free elements, their oxidation states are 0. By free elements, I mean it's not combined with other elements. And then I'm going to go ahead and determine the oxidation states of each of these individual elements. Oxygen is always -2. And I'm going to do a little bit of side work on the bottom here to show you how we can determine the oxidation state of iron. I have X, which is my iron, 2 times X because there's a subscript 2, not because there's a coefficient. 3 oxygens and -2 to represent the oxidation state of oxygen. And notice the coefficients do not play a role in determining the oxidation states. So iron's oxidation state is +3. And what we notice is that iron goes from an oxidation state of 0 to +3. It becomes MoPo, Mo positive, and then oxygen goes from 0 to -2. And so now we have identified our oxidized and reduced species. So here's a helpful hint. It turns out that all single replacement and combustion reactions are also redox reactions. You don't really have, if I just asked you which one's a redox reaction, you could memorize that statement and figure it, or work it all out like we have been in these problems. And if you notice that the oxidation states change, then you also know it's a redox reaction. So here are some more practice problems. I would advise you to practice them first and then keep watching to identify the oxidized and reduced species. I'm just going to go ahead and click through here so that you can have these extra examples to work off of. In this case, sodium is oxidized, chlorine is reduced. And here's practice B. This is a little bit different. Actually, it's a lot different, but we do know how to handle oxidation states for these ions. So we're going to determine the oxidation states. And in this case, the oxidation number is going to be -1. It's not a free element. It does already have a charge, so we go ahead and take the charge of that to represent the oxidation number. So these are pretty obvious. And now we need to work with this. We know that the oxygen here is -2 always, and I've done the calculation there. I forgot to put the oxidation number on top of oxygen there. Oh, actually it doesn't need to be done because we are only dealing with manganese and an iodine to see its oxidation states change. And what we have here is We have an oxidation state of +7 changing to +2, and then -1 changing to 0. We have our reduced and oxidized species. I really wouldn't worry too much about an example like this. We're trying to keep it simple. This is more of an advanced type of problem, so really don't worry about the complexity of this one compared to the others.